The rise of artificial intelligence gives birth to so many opportunities and technological advancements. But with its benefits come significant security vulnerabilities. Today, I speak to Mathieu Sinn, Senior Technical Staff Member and Manager of AI Security and Privacy at IBM. Dr. Sinn's research is primarily focused on the intersection of machine learning and statistics, including large sample theory and time series analysis. He has worked on order statistics for time series and determining the robustness of deep learning classifiers. Today, Dr. Sinn discusses his team's work on adversarial robustness within trusted AI.
Thank you so much for joining me today, Mathieu. And first, I'd love to start out by hearing more about your research at IBM and trusted AI.
Thank you, Anessa, for having me. And so my team and I, we're part of a global team within IBM Research that's looking into the security of modern AI systems. I think the motivation for our work is really the discovery over the past couple of years that AI, having great potential to solve important societal and business problems, has certain vulnerabilities that an attacker could exploit for their benefits. And that really relates to what we call adversarial robustness of AI and machine learning models in particular. So perhaps the most well-known phenomenon in that regard are so-called adversarial examples. So those are small changes to the inputs of a machine learning model, which completely alter its behavior and totally compromise its integrity. So for instance, think of a state-of-the-art image classifier, which normally you would feed it an image and it would tell you what the image shows. So it would come back with a category and it would show, for example, this image shows a panda bear. Now, an adversarial example has been crafted by an adversary in such a way that to a human, it would look identical to the original input, but there's a small difference. So maybe a few pixels have been slightly altered, and that will completely offset the machine learning model, and it will misclassify the input, and the attacker could even make the machine learning model output any particular class they wanted it to output to help them in their kind of malicious endeavors.
Awesome. So are there specific types of attacks? You mentioned that attack with the image classifier. Are there more specific types that the toolbox aims to combat or specifically targets? Just like to hear more.
You mentioned our toolbox, which is then the main project that we've been focusing on over the past 2.5 years or so. So that's the Adversarial Robustness Toolbox, in which we've compiled a broad set of state-of-the-art attacks and baseline defenses, with the idea that would allow researchers and developers to really test the models that they're developing, test the models that they want to deploy to see how vulnerable their models are against these type of attacks. And I think you mentioned images, and also the example that I used earlier was images, but in fact these threats apply to pretty much any type of supervised machine learning models and also other input data types. So it can also apply to, say, audio inputs. So when you have a machine learning model that automatically transcribes audio into text, it applies to models that analyze video data, etc. But even to more kind of conventional machine learning models and tasks like structured data, classification, or regression, even on those, these threats exist. To your question about what type of attacks they exist, I think the most important distinction is perhaps between so-called white box and black box attacks, where in the white box setting, and that's a common way in the security community to analyze threats. In the white box threat model, the attacker has complete knowledge of the model that they want to attack and that they want to fool. So if this is a neural network, they would know exactly what's the architecture and what's the weights of all the neurons in the network. And so they can exploit their complete knowledge. And there exist very powerful attacks that in most cases, if no defense is put in place, will bring accuracy of those models down to 0%.
Oh, wow.
And the other type of models, the so-called black box models, in that setting, the models are a black box to the attacker, so the attacker does not have a lot of information about the internals. But even then, it's been shown that for example, by probing the model a bit, or by using a surrogate model and then transferring the adversarial examples, the attackers can still oftentimes achieve their objectives.
So are there specific types of attacks? You mentioned that attack with the image classifier. Are there more specific types that the toolbox aims to combat or specifically targets?
Yeah, you mentioned our toolbox, which is then the kind of the main project that we've been focusing on over the past 2.5 years or so. So that's the Adversarial Robustness Toolbox, in which we've compiled a broad set of state-of-the-art attacks and baseline defenses, with the idea that would allow researchers and developers to really test the models that they're developing, test the models that they want to deploy to see how vulnerable their models are against these type of attacks. And I think you mentioned images, and also the example that I used earlier was images, but in fact, these threats apply to pretty much any type of supervised machine learning models and also other input data types. So it can also apply to, say, audio inputs. So when you have a machine learning model that automatically transcribes audio into text, it applies to models that analyze video data, etc. But even to more kind of conventional machine learning models and tasks like structured data, classification, or regression, even on those, these threats exist. To your question about what type of attacks they exist, I think the most important distinction is perhaps between so-called white box and black box attacks, where in the white box setting, and that's a common way in the security community to analyze threats. In the white box threat model, the attacker has complete knowledge of the model that they want to attack and that they want to fool. So if this is a neural network, they would know exactly what's the architecture and what's the weights of all the neurons in the network. And so they can exploit their complete knowledge. And there exist very powerful attacks that in most cases, if no defense is put in place, will bring accuracy of those models down to 0%.
Oh, wow.
And the other type of models, the so-called black box models, in that setting, the models are a black box to the attacker, so the attacker does not have a lot of information about the internals. But even then, it's been shown that for example, by probing the model a bit, or by using a surrogate model and then transferring the adversarial examples, the attackers can still oftentimes achieve their objectives.
Oh, geez. Well, now I read your article that is called Closing the Backdoor in AI Security that you co-authored. I'd love to just learn more about specific attacks. Can you describe the Jacobian saliency map attack that you were talking about, and maybe a specific example or that resulted in, like you mentioned, the image classifier, just the slightest change results in a total misclassification?
Yeah, the Jacobian saliency map attack was originally designed for images, and what makes it special that it really minimizes the number of pixels that the adversary has to alter in an input image. in order to change the behavior of the classifier. So for instance, like on a high resolution image, something like 300 times 300 pixels, in many cases the attacker has to alter, in fact, only just about 1% of the pixels to completely offset the model.
Wow.
And yeah, this technique, so the saliency map techniques, we've also have algorithms in our toolbox that apply that to other types of data. For example, we have a notebook in our toolbox which demonstrate on video data. So it's a 32 frame video segment.
Going back to the toolbox, does the toolbox only deal with deep neural networks or other types of algorithms as well?
Support other types of algorithms and models as well. We started initially with deep learning models, kind of in all the popular frameworks, so TensorFlow, Keras, PyTorch. But then throughout last year, we extended the toolbox to also support more conventional machine learning frameworks like scikit-learn, XGBoost, so things like random forests, logistic regression, models that in particular then are also the most common models still used on structured data, because we wanted to make the toolbox applicable to other domains as well, and more structured inputs as well.
Based on your total opinion, what do you think is the scariest example, at least maybe that you've seen so far or you predict, of an adversarial attack?
And of course, what you mentioned earlier, these examples like with vehicles and object recognition systems in vehicles, that's scary if you think about it. Also, since I think what's really scary about those scenarios is that the adversarial attacks were actually mounted in the real world. So as you said, it's literally what they demonstrated in the setup, that when they stick a yellow post-it note on a stop sign, which is a really simple thing to do, that would offset the particular machine learning model that, of course, that they had poison and that they had all the access to. So I find that definitely is a very scary scenario. I think probably, where we see these attacks really happening already is in the cybersecurity domain. Because if you think about it, like, for example, detecting spam emails or phishing emails or detecting malware, there a lot of AI is being used, and more AI and machine learning is being used to make these systems smarter. But then, on the other hand, that offers attackers a new attack vector, where they can now use these adversarial machine learning techniques to programmatically bypass an intelligent antivirus software. And there are a few reports already that this actually has happened. And there are a few vulnerability nodes already out there that kind of flag real antivirus systems as vulnerable to these types of attacks.
Going into more of the specific attacks or the categories of attacks, can you explain the difference between evasion attacks and poisoning attacks?
So an evasion attack, there the adversary tampers with the input of the machine learning model. So for instance, what the examples that we discussed earlier, change a few pixels in an input image so that the classifier will get it wrong. In a poisoning attack, those happen at training time.
Okay.
So while or before the machine learning model is actually being trained, there the attacker inserts poisonous samples into the training set, and that will then lead to the model during the training, picking up wrong clues, and then what's often referred to as backdoors that then the attacker can later on exploit in an evasion attack to more efficiently or more easily mount an evasion attack. So for instance, traffic sign scenario with the yellow post-it note, that was a combination attack such that it was particularly sensitive to kind of any yellow patch within an image. So it had learned the wrong clue that whenever I see a a distinctive yellow patch within the surrounding, then it's got to be a speed limit sign.
Oh, wow.
And then that then made it so easy just by putting this innocuous post-it note onto a stop sign. The machine learning model said, great, there's this yellow patch that I learned about, so this must be a speed limit sign.
Oh, wow. Are there specific machine learning algorithms that evasion attacks, let's say, or poisoning attacks work better on or work best on?
It's actually been shown that on almost any type of machine learning model or deep learning model, these threats apply. So that it does not really matter what exactly the architecture is of the neural network. Most of the cases, the attacks are equally strong. Now, of course, there exists then specific defenses that one can deploy, which is often a combination of two things. So changing the architecture and typically expanding the architecture, and then changing the training protocol. And the trick is really to basically show the model while it's being trained adversarial examples, so that the model kind of sees the worst case inputs that an adversary might present to them, so that they learn to be robust and resilient against those.
Okay. Oh, wow. So now going back to you and your research, what would you like to see, at least in the security realm, of trusted AI going forward? And as much as you can share, what are you working on currently?
I mean, one thing that we're working on is really to develop the algorithms and really the end-to-end tooling that allows software developers within the life cycle of, say, AI models to make sure that the AI models that they deploy are secure. Because it seems there's a bit of gap. I mean, there is like established processes and tooling for kind of more traditional software engineering and kind of like the type of threats that you encounter when you deploy web applications. But kind of this, how to really deal with complex AI components in modern software systems and web applications, there's still a gap there that we want to address. And that requires, basically automating a lot of how to exactly configure an attack and really figure out what's the worst thing that an adversary could do to me and my system. And so to have visibility on that. I think ultimately what the existence of the adversarial examples has shown is that deep neural networks, they work very differently from the human brain and the human perception. I mean, kind of when kind of deep learning really took off, that's what many researchers believed. Okay, these methods are so successful because they work very similar to the human brain. But clearly, if you see two images and to a human, they are identical, but they completely break an AI model, then that shows that that's not the case. And I think there's an interesting realization, I think, now in the larger deep learning community, that in some sense, current deep learning and representation learning is broken, you could say, and that to a large extent, modern deep learning just picks up clues which can be misleading. So I think this is really it motivates really rethinking about what deep learning is and how to combine deep learning with other AI techniques like reasoning or causal inference to come to learning systems that come closer to how the human learning system works, and which are equally robust and can handle ambiguity and ultimately make better reasoning, perception, decision making, etc.